Good morning, everyone. So last time we talked about sort of how to calculate marginal probabilities for these sort of spin systems on trees. And in terms of the belief propagation equation, so we had this sort of the message from, say, W to W prime is sort of the probability, is sort of the marginal probability at W when we remove the edge from W to W prime. And today I want to start off by sort of showing that if we calculate all these marginal or all these messages, then there's a simple way of calculating the partition function, the normalizing constant on the tree as well. And so I'll define phi v and phi on a vertex v and phi on an edge like this. And basically this is what this formula for phi v says is it's just...
Should it be phi or I? Because in your formula...
Oh, okay. Yeah, even though I spent sort of 5 minutes at the beginning getting everything right, okay.
That was just to see whether we were following.
Yes.
Yeah, or if I was following, or yeah. So this is log of zt minus log of zt minus the vertex v. So this is sort of if you rip v and its neighboring edges out of the graph, how much does log of the partition function change? And this is basically exactly the calculation we did yesterday. And the second one is what you get if you rip the edge w prime out of the graph, how the log partition function changes. Okay. So we keep the vertices, but we just remove the edge from w prime. Okay, and the formula says, okay, the log of the partition function is just sort of the sum of the sort of the contribution from each vertex. But each time we remove a vertex, we remove the effect of all of its edges as well. But each edge is in is next to two vertices. So if we're adding up the effect of all the vertices, we're sort of adding up the effect of removing each edge twice. So then we need to sort of subtract off the effect of adding off each of the edges because we've done it twice. So this is sort of in sum, it's like you want to remove each vertex once and you want to remove each edge once. And so you get to this formula. And that may sound like, rubbish, but we'll see that this actually, indeed is the, a theorem. Okay. Okay, and one can just do it by induction. So is induction on n, the size of the graph. When n equals 1, okay, the tree is a fairly boring tree. So there's no edges, so you don't have this term. The partition function is just the sum of psi bar of a at the vertex. And this is also, and so log of this is also psi of v in this formula, because there's no product here. Okay, so n equals 1 is easy. And now we want to, so we'll assume it up to n minus 1. So imagine we have a tree T with n vertices. And now I'm going to pick a leaf, and I want to sort of remove that from the graph. But I want to remove it in a way that doesn't change the distribution on everything else. So, I mean, that's, like we can think of this spin system as, a joint distribution on n variables, and I want to move down to a joint distribution over n minus 1 variables. So, so the way you do that is you just sort of sum over the possibilities of the nth variable. That's how you would take a marginal. And in the formula, that's like sort of summing over the contribution in the weight of everything that involves u. And because it's a leaf, it's only the vertex term, the one vertex term, and the one edge that it's in. And we can incorporate that into the function on its one neighboring vertex v. So I'll change the weight on v from psi bar of a to psi bar of a. Maybe it would have been better to write it as so psi bar of a, and then sum over, and then sum over the possibilities for u of psi bar of au, psi, and then psi of the edge from au and a. And if we do this, then we don't change the partition function. So this new spin system on this tree with one less vertex. So all of the psi's are the same except for the one at this neighboring vertex. The partition function will be the same. The joint distribution of the spins on all of these vertices will be the same. And because the joint distribution is the same, the messages will be the same as well. And because the messages are the same, these phi's will also be the same. So if I write log of zt, it's equal to, and in this second one, I'm just going to have everything with a tilde on it. So because of the way we've constructed it, they have the same partition function. And by induction, because this has n-1 vertices, sum over u and t tilde, oh, sorry, w and t tilde, v. Okay, but I said that because they have the same joint distribution, all of the phi tildes are the same as the phi's. So this is w in t. IV. The only difference is that there's one vertex and one edge that appears in t, but not in t tilde. So phi of u minus phi of u. So we've just got to check that this is 0, and then we'll have the formula that we want. Okay, so that removing this vertex and removing this edge will give us the same effect. Any questions about Ramon, your...
I still don't understand why this is the same.
Why this last equality, or?
Where did the extra vertex come from in induction?
So I mean, so this is from our inductive statement.
Right. So t tilde doesn't have units, right?
Oh, should that be a plus?
Oh, that would help.
That, yeah, okay. So it's no. So sorry. This is so if I subtract off phi u from this, then I just get the sum over the vertices in t tilde. Right. And if I subtract off this, then I just get the edges in t tilde.
But you claim the log of zt. In the original, you claim the log of zt did include u.
Yeah. So so this is not the end of the proof.
Oh, good.
So what I was saying
I
is,
thought you claimed you had finished. All
no,
right.
no, no. What I meant was that if this term here is 0, then I'm finished, because this is the right-hand side of the statement. Okay.
So it's suspicious, because then by induction, log of ZT would be 0.
Okay, so
There must be a different phi somewhere here, right?
I think last sentence should be omega in T tilde and plus those in the bracket.
so the last
So this should be sigma over omega in T tilde,
sigma.
and that's the plus.
Oh, yeah. Oh, yeah. So in this one we have in T tildes.
Yes, and then you change the phi tilde to phi.
These are tildes. So this one, everything is a tilde.
Yeah.
This one, I want everything to be without tilde. Okay. Okay. So.
Because if you remove
Oh.
minus, then log that T should be this.
Okay, yeah. So okay. I am. Okay. Yes. So why is this suspicious that this is 0? So there was one thing that I wanted to also assume, which was, let's assume that for the vertex u, psi bar of u, that these sum up to 1. Okay, so why can I make this assumption? Well, if I multiply all of these psi bars by a constant, then I'm not changing the distribution. It's just sort of every configuration gets scaled by the same factor. It does change the partition function. So if I multiply all of these by lambda, then I'll change the partition function by a factor of lambda. If I look at how it would affect the phi v and phi of an edge, it doesn't come into phi of an edge because there's no psi bars in here and it doesn't change the distribution, so it doesn't change the messages. The only place it would come in here would be here, and you would end up adding a factor of lambda here, so you would increase for the vertex u, you would increase it by plus log lambda, and you would increase log of the partition function by the same amount. So I can, without loss of generality, assume this. And what this means is if I look at the message from u to v, this is just of a. This is psi bar of a, sum of a prime, psi bar of a prime, which is, and because the denominator is 1, it's just the same as psi bar. Okay. Okay. So now you should be a bit suspicious that sort of since I haven't, by assuming this, it shouldn't change anything. So why should it change the proof? Why should this help in the proof? It should help because I sort of cheated when I said all of the phi tildes were the same as all of the phis. There's one place where they could be different, and that's at the vertex v. And at the vertex v, so phi v will be sum over A. I don't know why I'm writing it out again, but it's just this formula. So what happens when we remove one of the edges from this formula? Well, I could, so let's write this as, so we have this product over W that's next to V, but let's say W not equal to U. And then I'll have the term that corresponds to U here. So sum of okay, so this is sum over AW. M from W to V of AU. Okay, so this part is exactly psi tilde bar. Oh, did I? Okay, maybe because M from U to V is the same as psi bar of U, because I've made this normalization. So with this normalization, this is exactly phi tilde V. All of the others are just the same because the messages are the same, but V is the vertex where you had sort of one less edge. But because of our normalization and because we can sort of incorporate the effect of this edge into the sort of field at the vertex V, then we get the same thing. Okay, so all that's left is then checking that this is 0. So I want to IU minus V. And okay, so phi U is log of sum over AU psi bar of U of AU sum over AV psi of AU AV message from V into U AV. And this the edge term is sum over AU AV to V of AU of AV psi of AU AV. Okay, and because again psi bar of U is the same as the message from U to V, then these are equal, so this is 0. And so we complete the induction. Good.
Here's my think about this tree. Pick an arbitrary root.
Yeah.
Then we can associate. Then we can one-to-one associate each edge with its vertex furthest away from the root.
Okay.
That allows you to merge these two sums, right? You can sum up the vertices at phi v minus phi e, where e is the does that make sense? Is the one for which v is the furthest away from the root.
Okay.
Now you're saying that all edges or all vertices that are leaves, those terms in that sum is 0.
So
You just seem to have proved.
yes, but
And then now, because the rest is equal to phi tilde has leaves again, so then all of the terms of leaves of that are 0, and then it seems you have proved that log of zt is 0.
no, because I changed the field at v.
Okay.
So okay. So if I sort of keep doing the, I mean, if I were to, okay.
Or you're saying that psi tilde no longer has this normalization as v, and so
Yes.
I see.
Yeah.
This is the key.
Yeah. So sort of really what I should do is sort of each time I pick some leaf here, I will sort of normalize its psi bar by pulling, so that will sort of add, we'll get sort of a log of the sum of psi bar out, and then, yeah, and so then we could keep doing that, and eventually we would indeed get 0, but would get the sum of all these extra terms along the way.
Log of ct is exactly the sum of those normalizations, and that's the secret.
Yes, yeah. So it's not obviously a false statement, but
in some sense, the normalization is misleading because everything is hidden in the normalization. Right?
yes. Okay. So this is a formula for trees. Doesn't work on other graphs, but sometimes it approximately works on other graphs. So we're going to see that this, and actually, but on other graphs you have to think about, well, what are the right messages to take? And so it's sort of like, you know, but on locally tree-like graphs, there's sort of a, okay, art/science of understanding when you can make this approximation true and how to do that. So that's, now the easiest case is when you have decay of correlation. Let's say we have a unique Gibbs measure. Then on say a random regular graph, so this is the will be the next theorem. So let's say on sort of the infinite deregular tree, bar has a unique Gibbs measure. Just to make my life easier, let's also assume that it's permissive. And so the unique Gibbs measure will come with sort of some BP fixed point M. Then if we let Gn be, I want to say a random deregular graph, but we could do it in more generality than that. Let's say deregular and locally tree-like. By which I just mean that the number of, like for any fixed k, the number of cycles of length k is little o of n. Then log of zg, let's say 1 over n, is equal to phi v of m. And by this I mean just, let me finish writing this. By this I mean this vertex formula where you stick m the fixed point into all of the messages. And psi will be a fixed spin system, so all the weights on all of the edges will be the same and all of the vertices will be the same, so it's just the same fixed psi there. So that's psi of a vertex M. So maybe I'll do. And psi of an edge M will be the edge formula with the BP fixed point. And so we have n vertices minus dn over 2 edges. And so if we believe this formula would hold, then this is what we should expect. And it turns out that when we have a unique Gibbs measure, this will be true. Yeah.
Can you confirm that when you say the fixed point, you mean for leaf propagation on the graph?
Yeah. I mean on the fixed. So on the infinite tree, there's one unique. Well, there's one unique fixed point, and it's translation invariant. So that one. Okay, good. Any other questions? So the proof is, well, let's say we have the graph Gn, and now I just pick a vertex V at random, and let's, okay, maybe to begin with, just assume that D is even. So it will have some even number of neighbors, and what I could do is just subtract, so remove V, and U1. So then its neighbors U1 up to UD now only have degree D minus 1. So I'll just sort of match them up in a random way. And this will give me a new D-regular graph. If I'm unlucky, it will be a multi-graph, but that won't happen very often. And I'll say this is Gn minus 1. And I just want to calculate what's the effect of this operation. So log of Gn. Well, it's locally tree-like, and I picked V at random. So if I take some ball of a fairly large radius around it, what I see should be a tree.
What is the logarithm of a graph? Function on the graph?
Yes. Okay, good. Thank you. Okay, yes. So with some very large radius around the vertex V, it looks like a tree. And now, because of uniqueness, whatever boundary condition I put on this large radius is going to have sort of a negligible effect on the distribution around V. So if I rip out V, then the effect on the partition function is just the same as, it's the same joint distribution as if it was a tree. So it's the same multiplicative effect on the partition function. So this really will be phi V of M. But then I need to add back D over 2 edges. Once I've sort of ripped out V, these are now the local neighborhood sort of looks like D trees where they're D-regular, except the root is except the roots have degree D minus 1. So the marginals here will be given by exactly M from the BP messages, and also like they'll be close to independent, because for any boundary condition I put on the boundary here, once I fix a boundary condition here, then they're conditionally independent, and their marginal distribution, conditional marginal distributions, doesn't depend on the boundary condition. So they're approximately independent with marginal m. And so when I add back in d over 2 edges, that will just be the same as phi e of m. Okay. So now we've gone from, and there's some error because, you know, these were not infinite trees locally, they're just radius r. But there'll be some, so there'll be some error epsilon r, which I can make as small as I want, as long as by taking r sufficiently big. Okay. So this is going from n vertices to n minus 1 vertices. And what, you know, I could proceed by just, you know, doing this operation over and over again until I get down to a graph of, let's say, little o of n, at which, and each time I will pick up this factor. The only problem with that is you've got to check that when I do this operation, removing a vertex one by one, it stays locally tree-like. And you can check that that's the case, you know, with high probability. But there's also you know, but the analysis of that is a bit trickier. So an easier way of showing this would be to, rather than remove one vertex, oh yeah.
So in this case, when we take away d,
Yeah.
the degree is uneven. So, for example, 5.
Yeah. What would you do there? The easiest thing is to remove 2 vertices. Then we'd get sort of 2 that are chosen independently. So I have a v and a v prime. With high probability, they're a long way away from each other. So and so the distribution in their local neighborhoods will be very close to independent. So then when I removed 2 vertices, I get 2 times this factor. And then I'd have to add back in d edges, and I'd get sort of d times the edge term.
This method seems solid to whatever you want to do. I mean, there should be something that says to you, you cannot go much farther than this, right?
Well, I'm going to suggest, so the next thing I'm going to, so I started removing 1 vertex at a time, and then to answer your question, I said, okay, we'll remove 2 vertices at a time. But actually, I think the cleanest way of doing the proof is to remove, let's say, epsilon n vertices at a time for some very small epsilon. So now we have a lot of vertices, but if epsilon is really small, most of their sort of balls of radius r around them are going to be disjoint. There'll be a you know, maybe order epsilon squared times n that overlap. But that will only be a negligible fraction. And so I can pick a lot of vertices at once, and then if I fix the boundaries on all of these balls, then conditional on those, they're all conditionally independent, and they all have you know, marginal distributions that are given by the Gibbs measure, approximately. Does that make sense? Or so then I want to rip out each of these vertices. So I'll go from Gn to, let's say, G prime n, which is where I subtract epsilon n vertices. And I'll be left with a graph now with lots of sort of hanging half edges. So I guess d epsilon n half edges. And then I'll just pick a uniform matching of these ones. And in doing that, we'll get Gn 1 minus epsilon. And the same approximation will say, okay, if we take log zg n 1 minus, oh, I just want log gn minus log zg n 1 minus epsilon should be epsilon n phi v minus phi d over 2 phi v. Plus something that's epsilon times, oh, okay. Maybe this should have been a delta. So plus epsilon n times delta, which will be a function of r, but also maybe a function of epsilon, because epsilon is related to how many of these overlapping balls that I have. But by taking r big and epsilon small, I can make this error. I'll make this error term small. Okay, so what's the advantage of doing, removing a lot of vertices at once at a time? My wife just came to check if I'd forgotten to bring something, but okay. So we can check sort of how the number of cycles in the graph changes. So
all of these constant, like, okay, epsilon is a big, but like the delta is not dependent by the degree.
Depending on the
radius peak and the delta, the error you get are not dependent by the degree.
this delta will depend on the radius we look at.
The radius we look at is, I have to take it like degree dependent, because we are at finite n.
So it will be sort of, if I want to make delta smaller than, 1 over a million, then there will be some sort of large enough fixed large r that I can choose and fixed small epsilon that I can choose to make it less than 1 over a million or less than any constant that I want. So that's, so the effect of r comes from the fact that, I say on a unique Gibbs measure, distant boundary conditions don't affect the root, but there's sort of, if you want the effect to be less than, 1 over a million, you need to take a certain radius for that. And if I want the fraction of overlapping balls to be less than 1 over a million, then I need to take a epsilon fraction of vertices sufficiently small as well.
So the boundaries you drew on the bar,
yeah,
the non-overlapping circles,
yeah, so,
are at distance r.
yeah.
But so why? I am not entirely convinced why they should be often non-overlapping, because surely this grows exponentially as.
Yeah. So there's so say I take 1 point, then there's d to the r vertices in that, which, as you say, if r is big, is a lot. What's the probability of having another vertex in there? Well, it will be about d to the r times epsilon. So each vertex is picked with probability epsilon. So the chance of finding another one in there will be about d to the r times epsilon. And if we make epsilon much smaller than d to the r, then you typically won't have another vertex in the ball. Or maybe I want a radius 2r to make sure that the balls don't overlap. So pick a vertex v, look at its 2r neighborhood. There's d to the 2r vertices in that. And if I don't pick any points in that, then nothing will any other points in this radius, then nothing will overlap this ball. Okay, and each of these points, so we pick epsilon n points in total, so each point is picked with probability epsilon. So the expected number of other points I pick here will be epsilon times d to the 2r. So the overlapping probability would be bounded by epsilon d to the 2r. And I can sort of, first take r to be sufficiently large, and then pick epsilon sufficiently small to make this probability small. And then I'll get just a small fraction of vertices that that we have to throw out because they're overlapping. Yeah, I don't know. Okay, yeah, we can discuss it after as well if you like. Okay, so to complete things, I just want to. So if ck is the number of cycles, I want to show that g in 1 minus epsilon is not very big. And so, well, I could bound it by the number of cycles that we originally had, plus the number of new ones that we create. So how do you create a new cycle? Well, when we remove vertices from the graph, we don't create new cycles. We can only destroy them. So it's only adding the extra matching of the edges that can make new cycles. Okay, and the only way you would do it is if I have some vertex, say w, and there's a path. There's a path from w of length at most 2k that sort of leaves some half edge around w. Maybe gets matched to another one. Maybe it keeps going. Maybe it goes through a few more half edges, and then comes back to another half edge that's also close to w. And this is unlikely because there's only say d to the 2k half edges that are close to w, and so the chance that your path sort of manages to, through one of these matchings, find its way back to a close by one should be very unlikely. It should have probability, sort of constant over n. And this is for a particular vertex, so the number that we add, on average, should just be order 1. Basically for the same reason that we only found order 1 number of cycles in, Erdős-Renyi or random regular graphs. It's because in order to close a cycle, you need to add an edge that brings you back to where you started. And such an edge will have probability about 1 on epsilon n in the matching. Okay. Yeah.
Is it true or not true that after you pull out a vertex and rematch these things that you now look like a D-regular graph on epsilon if you're drawing uniformly from D-regular graph?
Yeah, I mean it will be. It's not. You don't get exactly the same distribution, but it's very close. Yeah. So for the yeah, so for if this was a random deregular one, then we could sort of analyze more easily the removing vertices one at a time. On a more general locally tree-like graph, the reason why I don't want to look at them sort of one at a time is that, in a sense, adding, like when I remove if I have a cycle and I take this vertex and remove it and then match up these half edges, it's possible that I end up with a shorter cycle. And so I mean, but it's also possible that these edges got matched somewhere else, so that doesn't always happen. But you have to worry about cycles tending to get shorter. When I remove a lot of vertices at once, and then I sort of can match up lots and lots of half edges, there's so much randomness in where all the half edges get matched to that you're very unlikely to create a new cycle. Because, well, I mean, to be more formal about this, I could start from a vertex W and sort of keep exploring out from it. And then, and sort of just follow some path in this tree. And then at some point, maybe I find an edge that's been removed. So this gets matched with somewhere completely different in the graph. And then I could sort of keep exploring from there. And maybe, so maybe my exploration keeps going over here. And now I find another edge that's been removed. And this maybe gets mapped somewhere else over here. Okay. But unless when I'm doing this exploration process, I find a vertex over here that sort of matches up with something close to our original W, then I won't create a new cycle. But there's only d to the 2k paths that I could take of length 2k, and if I'm exploring these, and this is the nice thing about creating a matching like this, which is that if I've revealed some of the edges in the matching, the remaining edges in the matching are just still a uniform matching. So the probability that, say, when I discover this one, that it gets matched back to something close to W, well, is still going to be about probability 1 on epsilon on n. So the probability of creating a cycle near W will be like d to the 2k times 1 on epsilon n. But there's n vertices W, so times n. So in expectation, we'll get maybe d to the 2k over epsilon. So just something that's order 1 in expectation. So the number of cycles only grows by a constant amount. So if k
is really small, then it's R.
If k is
constant.
Yeah, k is constant. Yeah. So really we only need k to be big enough to be bigger than the R here, or maybe 2 times R. Yeah, exactly. So certainly we can have long range cycles, although actually if I did a more thorough job of this argument, it would say that even up to sort of like a small constant times log n, we don't see many cycles of that length. Good. Okay, so when we go from, so if we start with something locally tree-like, then we remove an epsilon fraction of the vertices, it'll still be locally tree-like. And then we can just sort of run the argument iteratively, like let's say j times, so we'll have n times 1 minus epsilon to the j number of vertices, and take j big enough so that n, or 1 minus epsilon is to the j is small, and then we'd get, I almost wrote log of the graph again. The n to the 1 minus epsilon to the j. Delta times n. And then once I get down to a sort of really small graph, then it's not hard to show that log of z g, or let's say log of z, 1 minus epsilon to the j is less than or equal to a constant times the number of vertices. And so by taking j big enough so that this is small, then this remaining term will be, we could make this little o of 1 and this little o of 1, and we get the theorem. Okay, so the tree formula, maybe I should ask, so sorry that was sort of sketchy, but any questions about that before? So
can we just take another redefinition for this?
So if it's not D regular, you mean? Yeah. So we could run a version of this, say, for Erdős-Renyi random graphs, or for so I didn't discuss this earlier, but you can take the configuration model that's not regular. So you just sort of specify a certain fraction of vertices have degree 1 and a certain fraction have degree 2 and so on. Then, okay. Then you have to be more careful, because when the tree that you get, so then the local weak limit of the graph is no longer a regular tree. So the message, the BP fixed point of messages are no longer constant. They can depend on the local neighborhood of the graph, which is no longer always the same. But you can still run this sort of argument in that case as well. But that will be more complicated. So but yeah, indeed, this generalizes to sort of other more general types of random graphs. In the case of Erdős-Renyi random graphs, it's what you would sort of the step. If I want to go from Gn d over n to Gn minus 1 d over n minus 1, well, one thing I need to do is remove a vertex, but I also need to increase the probability of each edge slightly. So it's sort of like removing one vertex, but also throwing in a Poisson number of edges at random. And you can, but you can sort of work out what the effect of on the log partition function would be. It typically won't be a so in the regular case, each time we removed a vertex, the change in the log partition function was almost always exactly the same. In this case, it will depend on the local neighborhood that you remove the vertex from, but that will sort of average out as we remove vertices one by one. So one can still sort of make a statement like this. Good.
But you have to do this on a case-by-case basis, or could you write down a general theorem that if you have a unique Gibbs measure and you have a local weak limit to that limiting tree, then...
There are general theorems like that, yeah. So it's not sort of like every example by hand. Yeah, good. Any other questions? Yeah. Oh, do you?
Take like a general configuration model, you still need some, let's say, yes,
I mean, of the degrees or of the, sure, yeah. So if you have a very heavy-tailed degree distribution, then that can, change things a lot. So yeah, that's true. Yeah. Okay, good. Dylan, did
Can
you?
you say just like a few words about how you'd actually make like a quantitative that because you have a unique Gibbs measure, then the effect on the boundary of large ball like doesn't say much. Like how do you actually?
Right. So so now I mean now the yeah. So the question was, essentially, how do things become more complicated because the different neighborhoods are different. So in particular, like if I could have a very high degree local neighborhood, and if my graph branches out a lot locally, then it may not be that a depth R neighborhood doesn't affect the root very much. So really, I should take R growing with n here, and you want to sort of say, so maybe R equals, let's say log n, or maybe square root log n. Okay, so this radius on an Erdős-Renyi random graph, you still expect to see something that's locally tree-like. You could ask, what is the size of the boundary here? Well, typically it will be like d to the r, but what's the maximum boundary size you could get there? Well, it will be at most an extra factor of log n. This is something that you can check. If you're in the case where the interactions are weak, then the effect of the boundary will be sort of decaying exponentially. So although you have a sort of bigger boundary than usual, you have lots of levels for there to be decay of correlation. And so you can, on an Erdős-Renyi random graph, you can sort of say uniformly in all of the vertices in the graph, if you take a, let's say, radius square root log n, then the boundary won't have an effect if you're in the sort of high temperature regime where the interactions are weak. That would be the sort of uniform statement that you could make. so that then when I remove this vertex, I don't have to worry about things at a further distance than this. And generally, if I want to know what, say, the marginal is at the root of a vertex, I may need to know things sort of quite far away, but on average, the approximation gets better and better as I get a larger and larger radius. And once I get to, say, something a bit bigger than log n, then it's just enough to look at those local neighborhoods in order to get a good approximation of the marginal distribution of a vertex and its neighbors. I don't know if that sort of answers. Did you have? Okay, good. Any other questions? Okay. Let's see how I'm going for time. Okay. So I'm going to skip something I was thinking about saying, but I'll just tell you what the result would be. So for the theorem, we assume that there's a unique Gibbs measure. But as we discussed yesterday, there can be more than one. So in the case of the Ising model, when d minus 1 tanh of beta is less than or equal to 1, then m equals a half was the only BP fixed point, and it was unique. But when d minus 1 tanh of beta is greater than 1, we had 3 translation invariant Gibbs measures corresponding to m plus, 1/2, so mu plus, mu free, and mu minus. So if we were to guess that this formula is still correct, then there's like 3 choices that we could plug in for m here. There's really only 2 choices. By symmetry, m plus and m minus will give the same thing. But the question is, should you have the free measure or should you have the plus measure? And it turns out that the theorem holds when you have m plus here. I mean, there's different ways of showing that, but well, okay, I said I wasn't going to tell you how to do the proof, but you know, you can essentially show that if you differentiate log of the partition function with respect to beta, this is you'll get z over sum of xu xv e to the beta sum of xu xv, and this is just the same as the sum of the expected value of sigma u sigma v. So the derivative, and this is the expectation where we take it at sort of parameter beta. So you can work out the derivative of the log partition function, and you say, well, how big could this be? Well, locally, around each pair of vertices u and v, it should look like a Gibbs measure. And among all the Gibbs measures, what's the maximum value you could make this expectation? Well, it turns out that if you want to, if I have a vertex u and v, and I want to put boundary conditions here that make them as likely as possible to be equal, then the best thing to do is just take the boundary condition to be all plus. So this is upper bounded by dn over 2 of under the plus measure of sigma u sigma v. So this is an upper bound on the derivative, but it turns out to be actually exactly what it turns out to be tight. And so if you have an upper bound on the derivative, and if I know, so I mean, let's say I have a function, and I know its value at some point, and I know its value at some other point, and I also know some upper bound on the derivative that says that it's the derivative is at most something, so it's less than or equal to the integral of the derivative. But if the integral of the derivative happens to match the other endpoint that I know, then it must just be equal to this function along that path. And I sort of know what the partition function is when beta equals, well, I know exactly what the partition function is when beta equals 0. And I sort of also know what the partition function will be when beta equals infinity, or something close to that, because it's there, the best thing to do is just have everything be plus or everything be minus. So I know the starting point and the end point, and I have a sort of an upper bound on the derivative, and that upper bound on that derivative upper bound is also equal to, or the integral of the upper bound on the derivative is equal to the difference between the starting point and the ending point. And so that means that the derivative will actually be equal to this. And so the main thing is just saying that actually, you know, the Gibbs measure that maximizes the agreement probability of two neighboring vertices is taking the plus or the minus measure. Okay. Yeah.
Could you just remind me maybe what is the goal of the proof now?
So the goal was, you know, here. Yeah. So the theorem is that Gn is equal to 1 over n So in the regime where d minus 1 tangent of beta is greater than 1, then the log partition function is given by phi of m. So if we plug in the messages m from the plus Gibbs measure, then that gives the right formula here. And so, I mean, so to actually prove this, you would check that the derivative of the right-hand side is equal to this over n. And that's something you can do with calculus and a little bit of manipulation of the BP equations. This is very specific to the yeah. So yes, yeah. So this is a very specific calculation, as Ramon said. Should also be true for the ferromagnetic Potts model. No. So, sorry, actually, the ferromagnetic Potts model is more complicated than this. But we do know the value of this, but only when d is even. And why do we only know it for d is even? Well, originally when I started telling you this sort of operation of removing things one at a time, said, well, if I remove one vertex, and then I can match up the d edges in d over 2 pairs. As was pointed out, you can't do this when d is odd. And somehow there are some inequalities that one could only prove when you're removing one vertex at a time and not two. So again, it involves some maximization of Gibbs measures, but there's, well, yeah, so, okay, maybe I won't get into that. But but even Ising model, antiferromagnetic, so a negative value of beta, we stop being able to do this. So when beta is negative but small, we'll still have a unique Gibbs measure, and we can do the same thing here. But maybe it's good to talk about what happens. So if we have now beta, is minus 1,000, what happens if we put an all plus boundary condition at level n? Well, when beta is negative, the system wants to make neighboring vertices have the opposite sign. So the next level will be mainly minuses, and the next level will be mainly pluses, and so on. So you get a Gibbs measure which is not translation invariant, but it's translation invariant if you shift by like an even number of vertices. So it's semi-translation invariant. Okay, but it's sort of saying that the thing you'd like to do is have essentially half of the vertices being plus and half of them being minus, and they're sort of the plus ones are only next to the minus ones. That only works if your graph is bipartite. So actually, you can run this same argument if I was looking at a random deregular bipartite graph. And you'd look at this sort of semi-translation invariant measure, and we would again get the right prediction. On the other hand, if we just have a regular or random regular graph, then as we send beta to minus infinity, it's going to concentrate on sort of the partition of the vertices that has the best cut. And as I said in maybe the first lecture, this is a harder problem than the one we're talking about. We don't even have a physics conjecture of exactly how big a cut you can have for a fixed D. It should be something that's full replica symmetry breaking, and so this is not something. So when beta is really small, or very, very negative, this is not something that we can just predict in a simple way like this. And so, one of the things that we want to understand is when is the log partition function given by sort of a simple formula like this, and when do you have to do something more complicated? Yeah.
Question, if I understand correctly, yesterday these were like extra amounts, and the convex hull was also like the fixed points. Are there examples where you have to put in the equation some combination of the measures? It's always like extreme.
Okay, so let's say, so when, I mean, let's say we're in the Ising model case. We have the plus measure and the minus measure. These are extremal. They're not a convex combination of any other Gibbs measures. When beta is big enough, the free measure is not extremal. So we can write it as a convex combination of other Gibbs measures. But those Gibbs measures are very much not translation invariant. It's all of their messages will be different. And it's just it's only when you sort of average over them that you get something that's nice and translation invariant. There's not the recipe for, what you should put in here when this sort of formula stops working for M being something translation invariant goes in a slightly different direction. And so maybe, it's not something I can answer well at this point. So I'll maybe come back to that in 2 or 3 lectures time and sort of hopefully give you a better answer. Okay, so, but yeah, generally what we want to know is when do formulas like this work? When do they break? And what should the answer be instead when they break? And well, we're still a bit of a way from getting to that point.
In the case of the thermodynamic schema, can you give us an intuition for the flux? I mean, the CGN is the free Gibbs measure on the graph. M plus is not the free Gibbs measure on the tree. So it seems like the large cycles are creating extra correlations that are causing the boundaries to look more like pluses.
Yeah. So I mean,
but if we start at a point in Gn where you're locally tree-like, then you go up to some level log n, you look like a tree or something like this, right? And then you have big cycles. So
yeah. So I mean, calling it the free measure, I don't on the graph, I don't think is quite the right way to look at it, because like when we look at the free measure on the tree, well, on the tree, most of the vertices are leaves, but you don't have any leaves on a deregular graph, because, as you say, neighborhoods keep expanding and eventually sort of loop round with cycles. So at least when, beta equals 10 to the 10, you can sort of check by hand that you must have either mainly pluses or mainly minuses. There's, otherwise, because it's an expander, you would just have too many edges disagreeing with each other. So if I have some sort of vertex here, then on the boundary, I must just have sort of on average mainly either plus or mainly either minus here. And so the effect of the outside should be one of these, either the plus measure or the minus measure. I mean, that's sort of, I don't know if that's intuitive, satisfactory as an explanation, but
wouldn't that even be true from UF? As beta is 10 to the 10, and UF is probably not going to be extremal. Probably it also will have this property.
No. So okay, so if you look at mu f, okay, if I look at a depth 2 or something, then indeed it will either be, with very high probability, it will either be all plus or all minus. But now if I take a radius that's sort of very, fixed beta and take a very large radius and look at, say, the boundary here, it will be roughly equal numbers of pluses and minuses. Because along each ray, you're doing a Markov chain which is symmetric between pluses and minuses. So eventually it mixes. So if you look at very large balls under the free measure, then it's roughly balanced between pluses and minuses. But under the plus measure, it's, there's a preponderance of pluses, and under the minus measure, it's more minuses. So if you knew that globally it's mainly pluses or mainly minuses, then you should guess, okay, it's either the plus measure or the minus measure. And the local weak limit will be sort of a half-half mixture of the plus measure and the minus measure. But actually, if but that's sort of when I average over all the configurations that you see. If I condition on the magnetization, the sum of the sigmas being positive, then the local weak limit will just converge to the plus measure. So if you condition on having positive sum of spins, pick a random vertex, look at its local neighborhood, it will look like the plus measure. And here we needed something, to prove this so all of the other results, we just needed that it to be locally tree-like. But this last one, you also need that the graph is an expander. And I said, maybe when we were talking about random graphs, that I would use the fact that the graph is an expander. Here is where we use it, that it's an expander. Because if we don't assume that, you could have a locally tree-like graph that's just sort of 2 copies of a random regular graph, and what's happening on these will be independent, and the theorem would still hold for that. But once you ask that it's an expander, essentially you can divide the vertices into ones that look like the plus measure and ones that look like the minus measure, and there has to be a small cut between the two of those. You can't have too many vertices that, if I just took a vertex, look at its radius R neighborhood, and classified it as plus if there's more pluses in the neighborhood and minus if there's more minuses in the neighborhood, then you won't be able to find many neighboring vertices where one is classified as plus and the other is classified as minus. And therefore therefore one of these two sets must be small because it's an expander. And so most neighborhoods will have to look like the plus measure in this case. Okay. So I have just 7 minutes left. Any other questions about this? I can, maybe tell you the direction we're going for next time. So another thing, so this was sort of one way of working out what, approximating what log of the partition function is, and to give us a sense of how many solutions there are. This quantity will be, at least if we're in a system that's permissive, it will be concentrated. The Z. So, and this will just be from sort of an Azuma-Hofting type argument. So if I look at expected value of log of z given fi, where fi is sort of the filtration where I just sort of form the graph by adding in one edge at a time, then the choice of adding in one edge is only going to affect the log partition function by a constant factor if we're in the sort of permissive case. And so this will be a martingale with bounded differences, and so the Azuma-Hofting inequality will say that log z is concentrated around its expectation. But this is not something that's easy to calculate. Log of expected value of z is easy to calculate, or reasonably easy to calculate. And we want to know if and in what circumstances we can reverse the two, because then this will give us a good picture of what the value of z is. And so next time I'm going to focus on, I guess, working out how you calculate moments of the partition function. Yeah.
Can I ask a question?
Yeah, okay.
On the concentration?
Yeah.
So is like, how do you prove it in the sense that like for Ising model, okay, but for maybe like spin system where you have like a darker model, very high degree of correlation between the... Right,
so I didn't, I said it in words, but I didn't write permissive, and this will be important. So indeed, this could be false if we're looking at something like colorings, because it could be that I have a graph, and my coloring in the graph, I have two vertices, u and v, and their colors are, if I look at all of the colorings in this graph, u and v always have the same color. And so if I add in an edge, I go from having maybe a lot of colorings to having no colorings there. So in random constraint satisfaction problems, adding in one edge can have a drastic effect potentially. And eventually, and if you start with a graph and just add in edges one by one, eventually you will get down to you'll add in an edge and then you'll have no more colorings. And the step just before you got to that point, you would have exponentially many colorings. So the last edge you add will have a really dramatic effect. Okay.
And this was the picture you drew with the decay that we see.
That was about the probability, but if I drew the, let's say, log of let's say 1 over n log of z as a function of d, and let's say we were doing colorings, then the graph will look basically linear up to a point. Then there'll be some threshold here. This is the point at which it stops being replica symmetric and starts being replica symmetry breaking. And it will sort of be non-analytic at this point. But it will still be, we'll still have a finite value. And then we'll get to the colorability threshold. We'll still have a positive value here. But after this point, we just have no more colorings. So we go, if this is S, we go from sort of e to the ns number of colorings down to 0 and that will just happen in one edge that you add in.
But this picture is true for the coloring problem or also for...
So, I mean, I should say this picture is conjectured to be true for the coloring one.
But I mean, some results are proven, right?
Yeah, so and this is, yeah, so, Yeah, and so this will be true, for instance, for random k-sat when k is big. Okay, so for something like colorings, this concentration may not hold. Although in the case of colorings, we'll find that log z still tends to be very concentrated. But that will require quite a bit more work. Okay, but you also mentioned like the hardcore model, and then indeed, and that one's permissive, and so if I have two vertices u and v here, they both have a probability of being 0, not in the independent set. And the probability of being 0 is always at least 1 over 1 plus lambda. So when I add in an edge here, then there's always essentially if this was 0, then it doesn't matter, and so I can only change the partition function by a factor of at most 1 plus lambda in each step. So the log change is still sort of order 1. Okay, and I think I'm out of time, so we should have the coffee break.